Please help me welcome up next Peter Gao, the co-founder and CEO at Aquarium Learning, a machine learning data management system that helps teams improve their model performance by improving their data sets. Aquarium helps users find and fix common errors like labeling errors, patterns, or model failures. Aquarium's customers include companies across industries like logistics, industrial inspection, agriculture, waste management, and more. Today, Peter is here to share why data curation is a key part of the model iteration, some common data and model problems, then discuss how to build workflows and team structure to efficiently identify and fix these problems in order to improve your model performance. Don't forget to drop your questions for him in the live discussion section below. Over to you, Peter.
Hello. So nice to see y'all. Just as a quick introduction, I am Peter Gao. I am the co-founder and CEO of Aquarium. And this talk is called It's the Data Stupid. So for you folks who don't understand the sort of obscure 90s political reference, basically I want to make the point here that if you want to make your ML system better, you should probably think about the data as a key part of that. And I will talk a little bit more in a bit. So just kind of like a quick introduction to me. I am the co-founder and CEO of a company called Aquarium. Basically what we do is we build tools for machine learning teams to basically help them improve their models by improving the data that they train on. So, beyond the sort of obvious, vested financial interest, I do actually believe in the mission and wanted to talk through a little bit more of it. Because previously to this, I worked at Cruise. I was employee number 18 there, built a lot of the deep learning stack there from the ground up. And I learned many of these lessons super, super painfully, especially after coming from a academic background at Berkeley before that, where I was just, like playing with deep nets in like the very early days, and got a sort of rude awakening to the reality of machine learning once I actually got to industry. So, quick overview, I think a lot of people talk about kind of like, for example, like, data-centric ML is the term that Andrew Ng uses. There is kind of like, the sort of like operation vacation concept that Andre is always, beating the drum about. And I think they're perfectly right about the ideas, and they've covered a lot of this in more depth than I will. So my goal in this talk is just to go through kind of like, the reasoning behind why this is important to focus on the data, and also just kind of get into more of like the tactical tips of how do we actually like, implement a workflow in which you make your data better and make your model better. So the first thing that I want to cover is, I think, a lot of people are kind of used to what I would call old school ML. This is something that I worked on previously at Khan Academy and Pinterest. And the very common tasks are things that have been, essentially pioneered by web companies in kind of the 2000s. So a lot of stuff is like forecasting, like in the future, things like doing search relevance and recommendations, things like fraud detection. And because these were kind of pioneered by the Facebooks and Googles of the day, like they operate on the data that is logged in the web app, which is usually structured data. So that's like stuff you can fit into a SQL database, like strings and numbers and timestamps. The other sort of key part of what happened with this style of machine learning is that you were essentially getting labels for free, from the perspective of the practitioner. Users would take actions on Facebook, and then you could kind of see like, okay, like, what are they clicking on? What are they not clicking on? And that's essentially the training data that you would use for like a relevance algorithm. Or for something like fraud, like, users can essentially like self-report, like this is like, something that is fraudulent or like, inappropriate or like whatever. And that's generating training data for you. Or like, for forecasting, you basically can predict the future, and then you just wait to see what actually happens, and then that generates that gradient or supervision signal for your machine learning algorithm. So like the stuff that was kind of popular back then to handle this type of data, this type of setup, was stuff like logistic regression, random forests, SVMs. Operating on this sort of structured data that could scale to like, massive, like, amount of web data that you get, flowing from like millions of users on your site every day. And so like the sort of emphasis of the work that people thought of as machine learning back then was, okay, we need to build data pipelines and data infrastructure to just be able to crunch all this data, train big models on lots of data, totally makes sense. That's fine. But a lot of it was also around feature engineering, because you get this structured data in the door. And so a lot of the sort of like advantages of like feature engineering was that if you provide a better representation to a relatively basic, oftentimes linear algorithm, that you could get a lot better performance. And so you spend a lot of time on that. The data scientists in particular are spending a lot of time on that. And the other thing is that like you could actually do things on the model code itself. And so, for example, like, a lot of companies have to deal with like sparse data when they do their classification or prediction task or whatever. And so like that is something where you could basically do a lot of experiments with different, like model types and see an actual lift in performance that was, quite considerable when you consider 0.5% of improvement to Google's ad algorithm will generate, like billions of dollars or whatever in value. So now you fast forward to like kind of like 2012 was like AlexNet, and like obviously it kind of went kind of ham from there. And so the modern day is like dominated, at least in terms of hype, by deep learning algorithms. And so the sort of tasks that people would do here are very different than what you would do in old school ML. You do stuff more on imagery, you do stuff more on speech recognition, you do stuff like translation for NLP. But the focus kind of is that you're doing a lot more stuff on unstructured data, stuff that does not necessarily fit into a SQL database because of how high dimensionality it is. And so this is stuff that you store as a blob in like GCS, or as like an MP3 file, or as a PNG, or like, whatever, right? And the other thing is that because you're doing these sort of tasks that are kind of more linked to, for example, physical activities with the unstructured data, you don't really have the ability to get data for free. Like labels do not come for free from user actions. And oftentimes you say, if you're trying to build a self-driving car to detect pedestrians, you have to go pay an offshore provider like Scale or Labelbox or whatever to go and get an army of offshore workers to go and look at your data and draw boxes around all of like the pedestrians in each image or something like that. And so you have to spend money on it, and you have to now decide, what do I want to label with the limited budget I have. More than that, now that you have this unstructured data, you have like more of an emphasis on neural networks, obviously with this sort of deep learning thing. And it feels like every new research paper is on neural networks. So that's obviously where the field has gone in terms of like the algorithms. But what that also means is that when you look at the sort of work of doing deep learning in a production context, you still have the emphasis on data pipelines and infrastructure. That will never go away, because you just need to like, crunch data. You got to train models at scale. You got to do monitoring. That's all totally going to, be the same. But then, like the sort of stuff that changes is now that the algorithms are kind of these deep neural networks that are often pre-trained on extremely large data sets, and they're worked on by like giant groups like Microsoft Research or whatever. Now you kind of have this setup where it's really hard for an individual machine learning team to improve on the model or on the feature engineering, because it's learning the features itself. And so as a result, like because that avenue of like working on the code is like somewhat less like impactful, you now have this opposite thing where you have the data, which now does not come for free, which means that you have to be like, okay, like what do I want to label next to maximize the improvement to my performance? Which means like you want to optimize for labeling things that your model like struggles on, or has like, problems with, or that is like rare, or that it hasn't seen before. And then also because there's a physical process in which like, human operations people are going and drawing boxes on things, you have to account for error that like these humans can make, and therefore you have to worry about the quality of those data sets. And so I'm going to focus on that bullet point for this talk. So, when I break it down, regardless of whatever algorithm you're using, if you're working on a supervised machine learning system, you don't really have like, too many levers per se to like, pull on to improve your model performance. Like, you can improve the model code. You can do stuff like, hyperparameter tuning. You can try like, random forest versus an FCM. You can try like, like changing, the model architecture you're using from YOLO to SSD, like that's, all stuff you can do on the code side. You can also do stuff to improve the quality of the training data set that this model trains on. And so working on those two things will get you like some sort of improvement most of the time. And then it's more a question of ROI and what you do in those sort of broad buckets. But the thing that I think people neglect to think about when they think about a production and a deployment is that it's not just about a model anymore. In research, you just produce a model, it gets state of the art, you publish a paper, that's cool, all right, let's move on to something else. But when you're in production and industry, you basically have to go and think about, how do I do this in a environment where I am constantly seeing change in the operational environment that my model is deployed into. And also, I know that the accuracy requirements to make a buck are a lot higher than maybe something that you may see in research. And so you want to be not only just dropping, here's my model, it has this performance, you also want to be iterating on this model. You want to be treating it less as just a single model and more as a model producing pipeline that incorporates the training code and the training data set. And you want to be able to cycle on this pipeline, improve this pipeline, improve the quality of the stuff that comes out of that pipeline, faster and more frequently. So that's really important. So, now I get kind of into more of the specifics or the motivation of this talk, which is why work on the data. And, the reasoning behind working on the data is because it's usually a really high ROI way to improve the quality of the sort of ML system that you're working on. So, of course, this example, I'm looking at this tweet. This is a very common story I've experienced in a few times where it's have some random choice of an algorithm, random choice of the data that you already have. And then when you work on the algorithm, you get these sort of incremental improvements to the model performance. But then when you work on the data, you get this massive, massive jump in terms of improving the model performance. And the reality is that there's simply just a class of problems or many different classes of problems that cannot be solved by working on the model code itself. And so as a result, when you think about the differences in the workflows between what you do in research and what you do in, more of a production context. This is a slide from one of Andrej Karpathy's talks a few years ago, where in your PhD, you're working with this fixed data set that is a reference data set, like ImageNet or COCO or whatever. You're just trying to optimize the algorithm to beat the state of the art on this data set. But then when you go to an industry context, you have the ability to collect and label more data. And so as a result, since there's so much ROI in improving the data, when you go to industry, you spend most of your time, you spend most of your attention, you get most of your pain from dealing with the data. And so now this kind of, is the sort of short, this is why you should work on your data. And now it kind of moves into okay, well, how do I work on my data, right? Because you kind of see a lot of talks about this idea of data-centric ML, but what does it mean in practice? And if you were to think about the overall workflow in your ML pipeline of how do I improve my data set, it is fairly simple, I would say. It's I heard this quote, how do you solve a problem? You look at the problem, you think really hard about it, and you write down the solution. And in this case, when you want to work on your data, go find the problems in your data, what's wrong with your data quality, or where are the places where your model is not doing well on your training or production data. And then once you find those problems, figure out why are those problems happening. Is it a reason of the data quality being bad, or is it a reason where the model is just not seeing a certain example that is very rare and doesn't know how to treat it? And then go and fix those problems, right? Either edit the data set, remove bad data, add in more data, the things that you want the model to get better at. And then as you retrain your new model on the new data set, you don't even need to change the code on the model. Make sure that this new model it produces is indeed better than the previous model, not only on the aggregate in terms of performance metrics, but also on the specific problems that you identified in the first step. And then once you do that, you repeat and you just kind of keep cycling to make sure that you, produce better models as you go through this loop. So when you think about the type of problems that you can encounter when it comes to your data set, there's a few different varieties of it. One of them is that your data itself is bad. When you're dealing with, for example, a physical process, like a physical camera that is capturing data, sometimes the camera can just mess up, have a hardware error, and produce distorted imagery or something like that. That's what you can see on this top right side as an example. And that's obviously something you probably don't want your model to be dealing with. You probably want to filter it out on the firmware side or something. Another sort of example is when you have labeling ambiguities in your data set, or if you have labeling errors in your data set, this can actually confuse the model. The model will just see different ways the same scenario is treated, and it will not know what to do. Or even worse, like, you basically evaluate your model on, your evaluation data set, and the evaluation data set is like, full of errors. And so the metrics are not trustable, which means that you're making bad decisions based on bad data, and therefore like you're gonna like go the wrong way. So on this right side, you can see an example of where, like, this is one of Andrew Ng's talks where you have like, these different defects in the sheet. Do you label them as like, one giant box over all the defects, which is what labeler 1 has chosen to do? Or do you label each of the little defects individually, which is what labeler 2 has chosen to do? And this sort of ambiguity can confuse the model. It can cause it to make errors and mess up its performance. Another example, it's very common, difficult edge cases. This is when your model encounters a case that's just hard. It's like if you study for a test and there's a topic on that test that you just don't really know that well, you're probably going to want to study more for it. And so in these sort of cases, this could be like, for example, in imagery, like a very like dark area or low contrast area. In audio, it could be like a lot of noise in the background. These are cases where the model legitimately struggles, and you just want to be able to collect more data so that the model can learn to get better at it. And then the last category of stuff is out of sample data, which is like, the model has never seen it before. It doesn't know how to handle it in production because it was never trained on anything like that. And so like, these are kind of the common things that you can basically look for and solve when it comes to improving your data set. The problem, like that sounds easy, right? Like, okay, cool, let's just go fix all those problems. But the problem is that you have a hard time finding these problems because, you have a lot of data in your data set. Maybe you have 1 million examples and maybe like, 1,000 to 50,000 of them are actually erroneous. And how do you identify those without like spending a lot of time? But the other aspect is that like most of the time when you do deep learning, you're dealing with natural sort of situations in which there are long tail distributions. Long tail distributions mean that, maybe like 80% of your data set consists of the most common case, but then the remaining like 20% may consist of like a lot of different, miscellaneous cases, so that, when you have a lot of like, these variety of cases that have very little representation in the data set, the model will typically not do well on these less represented things. So this is, like a link from the A16Z blog post about the economics of AI, which is like, you need to deal with these edge cases if you're going to get to a performance level that is usually acceptable to surpass a human's accuracy, or to like, have some economic value in a production deployment. So you have to tackle these edge cases. But the difficulty is that these edge cases are rare. How do you find them? How do you identify them? How do you like fix them? And that's like a whole thing. And so you have this problem now of like, okay, if I want to go and find bad data, I want to like find the invalid data, I want to find the labeling errors, like, how do I do that in a way that doesn't require me to go look through all million data points in my data set just to find the 1,000 to 50,000 that are actually messed up? And the other thing is like, when I have some pattern of model failures where I identify this as an edge case in the model performance, this is a place where it's difficult or it's like never seen something before, like how do I identify those clusters of things without having to look again through the entire data set? And the dumb way that people did this before was like, let's just hire a bunch of people to go look through the entire data set. You have like this haystack, of like the data set as a whole. You have a needle of like, this one error that you're looking for, and you're just going to hire a bunch of people to dig through the haystack, and it's very expensive and labor intensive. But the solution that I think people don't think about, this one weird trick that labeling companies hate, is to reduce the search space in an intelligent way by letting the model tell you where in the data set to look. So instead of you having to manually look through millions of data points, you instead can just filter down to the places where the model highly disagrees with the data. These high loss disagreements actually are usually labeling errors, and that's a great way to surface like, the needle in the haystack. And another way is that if you know that, for example, your model has a bunch of different errors where it disagrees with the data, but there are certain edge cases or on the long tail that are like, concentrated in there, you can in fact actually let the neural network tell you what clusters of similar data it thinks exist in the sort of like, distribution of the data set, and allow you to basically find the edge cases in the data set as grouped by essentially similarity in the neural network embeddings. So this kind of gets into the sort of shameless self-promotion aspect of this talk, which is, well, you're going to need some tools to do this. And so I'm just going to use like a few practical scenarios that we've seen from working with some of our customers and looking at open source data sets, from working on Aquarium, that may be very valuable tips of how to find and fix these types of problems. So one example is if you were to look at a lot of different open source data sets, you just like can stumble onto labeling errors very quickly. And instead of you having to go and look at like, oh yeah, here's the million data points, you can instead just like look at, okay, here's the places where my model and my data disagree. In this case, here are like, false positives where my model detected a car where there's like, no label before. And lo and behold, when you sort it by loss and see the places where the model is most confident, these are places where there are actually cars that were not labeled in the kitty data set, which is like, okay, cool, like let's go fix them now, right? And so that's a really easy way to find this stuff. This also applies to different modalities. Kitty not only has imagery inside of it, it also has 3D point clouds corresponding to camera imagery in it. And so when you look at the bottom, the labels are all in 3D, and you can see all these like different bikes and cars and stuff that like are labeled in this very dense urban scene. But you want to be able to like kind of dig through the haystack and find the needle of like, here's the place where the labels are messed up. And when you sort by loss and find, okay, well, here's like a high confidence, detection by the model here in purple, this is actually not labeled. But then when you actually look at the point cloud and correspond it to the image, which is kind of this guy in the black coat over here, there's in fact a pedestrian there who's just not labeled by the human annotators who assembled the kitty dataset. And so this allows you to really quickly surface problems and fix them. Another example that kind of stretches across modalities, I did a hackathon project about a year ago on this data set called the speech commands data set. And I just wanted to see if I could take like an audio data set and train a very simple model and just work on the data. Like how much improvement could I get to the model? And so this data set consists of basically these 1-second audio clips where a human speaker is saying a word. So in this case, they are saying the word bed. And the task of the model is to try and identify like what is the word that is being said. And so you can kind of look at Aquarium, and you have these spectrograms on the top, and then you have waveforms on the bottom that kind of describe this audio data. But again, you have this problem of like, how do I go and actually do error characterization of this model so that I can decide what I should do next to improve the data? And it turns out we can actually use embeddings that we extract from a very simple machine learning model that we've trained on this data, like a 1D convolutional model. And you can basically get a distribution of the data in the data set. You can see here like are all these different clusters of similar data. Here are outliers in the data set that may be a little bit farther off. And you can just kind of understand the distribution of the data set. But then you can also go to the next step and say, okay, cool, I now understand the distribution of the data set. Now show me the places where the model and the data disagree. And it turns out that all of these sort of green areas are places where the model and the data agree. And then the red areas you see over here are the places where the model and the data disagree. And they're all kind of concentrated into this one section. So like it's all kind of basically like a similar sort of pattern of failures going on in this part of the data set. And you can even remove the agreements and just look at the disagreements, and you can just see the density of all the sort of errors over here in this section of the data set. And basically, if you dive into this, and of course, this is all using Aquarium stuff in terms of the tooling, but you dive into this, you can lasso this group of points that represent individual audio clips and understand kind of what is happening in this part of the data set that is so concentrated with errors. And it turns out that the reason why that these errors are happening is because these audio clips are supposed to have a human say something in that clip. But there are just a lot of audio clips where either nothing is being said, or the person is just starting to inhale and say the first syllable of the word just as the audio clip is ending. And so the reason why this is structured like this is due to some peculiarities in the way that data set was assembled, the way it was labeled. But what it manifests as is you as a human being able to listen to these clips and having no clue what is being said. And so if you as a human can't tell what is being said, then how can an algorithm tell what is being said? And so this is basically a problem with the data set that you can treat in different ways. You can either remove it from the data set entirely, or you can say, oh, this is an invalid or an unknown class or something like that. But this is how you improve the data to solve basically a practical machine learning problem. Another thing I want to go into, these are kind of problems with the data set, the underlying, way that they were labeled and all that. But there's also kind of the idea of like, how do I identify edge cases in the model performance and go and basically get more data of those edge cases and label them so that my model can retrain on those edge cases and get better at those edge cases. And so again, we come back to this problem of like, each natural distribution of data is a very long tail. And so we want to be able to find what is in that tail. We want to find the patterns. We want to find the sort of like groupings of edge cases and be able to identify them and collect more data specifically for them. Because if we just uniformly sample data, we're not going to like, we're just going to get more of the majority class, which the model likely already does well on. So what you can do is you can use embeddings to not only get a sense of what is in your sort of data set distribution, but also kind of get a sense of like what is the relative frequency of this. And so this is basically a UMAP plot of the embeddings for this data set that we worked on, which is the Oxford IAT pet data set. It's just a bunch of images of like dogs and cats, and then the task is to classify these images as like, is it a Shiba Inu, or like is it a Pomeranian or whatever. And so you can basically see this is the class of Shiba Inu. And even for Shiba Inu, you see that there's kind of some variation in the way that these data points are distributed. There's some outliers that are different from the core cluster of Shiba Inu. And when you look at that core cluster of Shiba Inu, you kind of see that Shiba Inus, for the most part, are orange coded. This is what we expect for like, when we think of a Shiba Inu in our heads. But as we explore kind of the tail of like, these different sort of subclusters of Shiba Inus, you'd see that there are in fact Shiba Inus with white coats, Shiba Inus with black coats, and like there's actually variation even within this class. And this sort of white coat Shiba Inu is extremely underrepresented, and the model tends to not do very well on it. And so what you can do is you can actually use embeddings to go and search for more examples of this edge case that you've identified. So not only are you using the embeddings to basically get a sense of the error distribution, but then you can actually do similar research using like cosine distance on these embeddings and look through unlabeled data and basically pull back here all the things that are similar in the embedding space to this set of like edge cases that I want to gather more data of. And so this is very appealing. And this is basically a set of like stuff that is similar in the embedding space to that like set of white Shiba Inus I just showed you. This is appealing because if you want to go and collect more data of an edge case and label it, the way that people do that right now can often be very manual. They can go and like, for example, in a robotics context, go send out the robot into the real world and then stage some data collection opportunities with like certain edge cases that you may want to collect more data of. But by using this, you can essentially use embeddings to search through all of your historically collected data and get more examples of that edge case, label it, retrain your model does better. So that was a handful. I think I probably went way over time, but I will pause here for Q&A and happy to just go into more detail about what I've seen in my previous ML experiences, things I've done over time, what we see from our customer base, and just provide more pro tips on how to do ML better. But yeah, hopefully you like this, and I'll pause here.